This is Jack Jackson back again. We're going to talk about introducing geometries today. We will consider a geometry to be a set of points along with possibly a set of lines and or a set of planes with a set of definitions and postulates. It then necessarily includes all the propositions and their proofs as well. So that whole thing, that whole system we're going to call a geometry. So a geometry is an axiomatic system. In the previous pages, you were introduced to the initial existence and incidence postulates for what we call neutral geometry, sometimes also known as absolute geometry. It includes both Euclidean and hyperbolic geometries. These postulates and definitions have been carefully chosen and ordered, as well as the propositions, so that we can develop both of these geometries simultaneously. The postulates that we have so far also hold in a geometry called taxicab geometry. So for the moment, the postulates work for all three of these geometries. At some point, we will split off taxicab geometry from the other two, and then at a later point, we'll split off Euclidean and hyperbolic geometries from each other. But for the most part, we're going to try to do one treatment that's going to go with all of these geometries as long as possible. Now, so I start throwing around these words, taxicab geometry, hyperbolic geometry, and so forth, and you may not have any idea what these are, and that's okay at this point. However, I hope that you're fairly familiar with Euclidean geometry. That's your basic geometry from your K-12 and university courses, including such things as, well, just middle school mathematics, high school geometry, which you may have actually had in junior high school, trigonometry, pre-calculus, calculus, those kinds of courses. You would have encountered a lot of geometry and a lot of properties about geometry. So for now, just note that these same postulates are axioms for not only that Euclidean geometry of which you're familiar, but also for multiple geometries, including Euclidean geometry. When we use the term neutral geometry, we'll include those postulates that are valid in both Euclidean and hyperbolic geometry, which turns out to be all of the Euclidean postulates except for the parallel postulate. So you've already done some reading about the development of these geometries and the attempts to prove the parallel postulate actually led to hyperbolic geometry. Now, we'll sometimes use the term unified geometry. Kay uses this a lot in his text, and it is based on a set of postulates which are valid in Euclidean, hyperbolic, and spherical geometries, and for the most part taxicab geometry as well. We have to modify some of these postulates, even some of the ones that we already have, to work in spherical geometry. Let me just go back here, and I can even tell you which ones. The first two are still good. In spherical geometry, we'll usually deal with only one plane, and hyperbolic geometry as well. So anything referencing planes doesn't really matter, but we could still accept number 3 and 4 and 5. But it's number 6 that gives us a little problem, because if in a sphere, as we'll see a little bit later on, a line is going to be a circle, what's called a great circle. It will be a Euclidean sphere is our plane, our spherical plane, and a Euclidean circle centered at the center of the sphere, the same radius as the sphere. That is a great circle on the sphere. We'll see that that's going to be what we mean by a line in spherical geometry. And of course, if you take 2 points that are on opposite ends of a diameter of that sphere, say the North Pole and the South Pole, say on the Earth, then there are infinitely many lines going through them. And so postulate 6 doesn't work. So we have to modify it. If we modify it a little bit differently and talk about these are called antipodal points, like the North Pole and South Pole. If we eliminate those, then any two distinct and non-antipodal points, then there exists exactly one line that contains both of them. With that modification, then postulate 6 is true in all these geometries. And then I think everything else we can keep. So it's just that one slight change, and then we have something that works for spherical geometry as well. We'll talk more about this next week. I do use a couple of abbreviations, IE and EG. I think you're probably familiar with these already. But IE is an abbreviation for the Latin id est, which is basically means that is, or in other words. EG is abbreviation for Latin exempli gratia, which means for example. Okay, so IE means in other words, and EG means for example. And I'll use one of those in the next paragraph here. Notice that the postulates presented thus far only deal with existence and incidence relationships, i.e. they either state the existence of some geometric figures with certain properties, or they are conditional statements, if then, which say that if certain geometric figures with specified properties exist, then other figures also exist with certain element or subset relationships among the given figures. So these incidence relationships are dealing strictly with subset or element relationships. They don't have anything to do with order, betweenness, or distance. And we proved in Proposition 1, actually after Proposition 1, we introduced a finite geometry containing exactly 4.6 lines and 4 planes, which satisfies this initial set of existence and incidence postulates. For they also, same postulates are true in neutral geometry, but they are also true in this finite geometry we came up with just this minimal number of points, lines, and planes. And but notice in that particular thing we had nothing to say about distance or order or anything like that. So we can explore several geometries with this same set of postulates. So we're going to prove what we can with these sets of postulates. When we've sort of exhausted that, then we'll add a few other postulates and see what we can prove with that. And in this manner, we're going to eventually get to the point where we'll eventually have all the postulates for Euclidean geometry, but we're going to try to keep things going as long as we can and prove what we can by adding a little bit of postulates at a time. Remember, when we specify a model for finite geometry, what we're doing is we're listing the set of points, the set of lines, and the set of planes. Okay, so lines and planes are themselves sets of points, so the set of lines is a set of sets, as is the set of planes. And so this list of sets is the model. The picture that we draw with it is an illustration of that model, and we're going to be building dynamic illustrations in Sketchpad a lot of the times as well. But be careful when you're interpreting illustrations. For example, we often use Euclidean line segments or Euclidean curves to indicate lines in the model, but don't necessarily think that these have to be parts of Euclidean lines necessarily, or that they're all there. So for example, when we did Proposition 1 and we have our model here, we used what's a Euclidean line segment to indicate that D and C were on the same line, but it does not mean that these Euclidean points here are actually points of the line. In fact, one model was where D and C were the only points of the line. And in the Euclidean case, it actually, of course, that line goes on forever. So every geometry should have at least one point in it. So we're not talking about the empty set. And of course, to do that, we'll need an existence postulate that says that there exists something. But they may or may not contain lines or planes. A lot of what we're going to be dealing with is planar geometry. In fact, most of the course actually. So most of the course, we're mainly going to be considering everything in one plane. So either you can think of planes don't exist, or all the points exist in a single plane. And so, in that sense, we don't really worry about the plane part so much. We're mainly worrying about the relationship between and among points and lines. Now, why do we study finite geometries? One of the things is we want to achieve certain goals. One is practicing writing detailed proofs. And we also want to gain a deeper understanding of exactly which combination of postulates lead to various results. And what happens if we change these postulates a little bit? What kind of different results could we get? And we want to gain a deeper understanding of the foundations of Euclidean geometry. We want to know why the things work in Euclidean geometry. If we know what we can get and what we can't get from certain postulates, then that allows us to go forward. And the main thing, of course, again, is practicing writing proofs. So we want to get better and better at writing proofs.